Hi everybody, my name is Glenn Lockwood. I'm a storage architect at the National Energy Research Scientific Computing Center, otherwise known as NERSC, at Lawrence Berkeley National Lab. Even closer. All right. And so my background is in dealing with Flash, so I was part of our burst buffer project on Cori, which is our current system. We were one of the first production large-scale parallel file systems based entirely on Flash. We recently, as of 2 weeks ago, announced our next generation system will be a 30 petabyte all-flash file system. And even before that, I worked right behind us here at SDSC on Gordon, which was one of the first supercomputers to integrate Flash at large scale. So my talk today will just walk through some of the challenges in deploying Flash and give you an overview of all the different places you can stick it inside your system to accelerate your workload in different ways. So this is kind of a model view of what your typical HPC system looks like. On the left, you've got your compute nodes connected with a high-speed network. This might be InfiniBand or Aries or any number of other technologies. You've got I/O nodes that are right in between the compute nodes and the storage, and these are where I/O from the compute nodes transit to reach the file system on the back end. And on the back end, you've got a storage fabric, which may be something like InfiniBand connected to storage nodes. These the red boxes here, which are like your Lustre OSSs, your GPFS NSD servers, or related things depending on which parallel file system you deploy. And the question is, if you want to integrate Flash into this and accelerate your workloads, where do you put it? And it turns out there's a lot of different places you can put it. For example, you could attach it to discrete servers that are integrated onto your compute network. So this is a model that I call fabric attached Flash. So you have a discrete server on the same fabric as your compute nodes. It has Flash integrated into it. And you can use this in a variety of ways. So going through the pros and cons of this, I would say this is perhaps the most flexible usage model. And all right, it is one of the most flexible usage models because your Flash is co-located essentially with your compute, but it's disaggregated. Okay.
Yeah, it's like this way, right?
All right, I'm going to rock out here.
Yeah, you're going to rock out.
All right. So it is one of the most flexible usage models because you have really close proximity Flash, but at the same time it's not directly attached to your compute nodes. So you can aggregate or disaggregate it in any way that you might like. It has the high locality between your storage and compute so that you can do many things with it. But because it is attached to the fabric and not the compute nodes, you still are susceptible to resource contention when you deploy Flash this way, because ultimately the storage traffic between your compute nodes and your Flash may compete with MPI traffic. In addition to that, because it is very flexible, you rely on a lot of software to actually deliver whatever functionality you want. So for example, the data warp product from Cray is an example of this architecture. And Cray has deployed a very thick software stack on top that makes this a usable form of Flash to the compute nodes. So in the absence of having some often proprietary solution to aggregate all that Flash and deliver it to your compute nodes, it can be quite challenging to deploy this. Another place you can put Flash is directly in your storage nodes. So this would be in your Lustre OSSs or your GPFS NSD servers. And this is actually a pretty popular thing to do in general. If you go out in the enterprise world, just about every single storage vendor will do this nowadays. One of the big benefits is this is entirely transparent to your users because it's a block level cache. So a user just interacts with the file system as they normally would, but their writes are actually hitting Flash rather than spinning disk and then asynchronously draining off. But that's also a downfall because it is transparent. The user has no way to express any hints about what their anticipated workload is. So they have no control over how this Flash asynchronously drains. So unless you're doing something that is already captured by whatever heuristics are baked into the storage design that uses this, you could run into a lot of problems. And typically because this is node local and it's attached to disk, you typically have very small Flash capacity in this configuration. It's really just a block level cache and not a whole lot more than that. But like I said, this is a very common deployment model. So DDN has its SFX accelerator where you deploy Flash directly in your DDN nodes. Spectrum Scale from IBM does the same thing in their ESS, and then Cray also has the NXD block caching. And it's all doing the same sort of thing. Very easy to use, but at the same time doesn't give you a lot of options to optimize. Another place to put Flash is logically between your compute nodes and your storage. So this is what we traditionally think of when we say burst buffer. So this is where it looks like you're writing to a parallel file system, but you're actually writing to flash in between, and it's asynchronously draining, but it's all a single namespace. So this is physically the same as the fabric attached flash architecture that I showed before at the beginning, but it's logically different in that the way you use it is it's fully transparent. The benefit of this is that you often do have some way to express hints to the burst buffer software that's in between that makes all this work. So DDN IME functions in this way, and there is a DDN IME API that you can use to be more intelligent about how you want your data to be sent to IME and then how you want it to be flushed, if at all. You could just say that I want this data temporarily written to the flash burst buffer in between and then never drained out because I know I'll delete it at the end of my job. And then you don't have to expend the bandwidth on the back-end network to actually asynchronously drain the data that you don't really want. And there's a lot of examples of this. This is kind of the easiest way to use it because the flash is just exposed as the namespace of the underlying file system. So for example, Oak Forest PAX uses perhaps the world's largest DDN IME installation that I'm aware of. And it does so in the exact same model. The Tianhe 2 China system in China also uses this model using their own custom software called H2FS. And just yesterday I learned Fujitsu, for its post-K machine, is developing a burst buffer software technology called LLIO, which functions the exact same way. So this is a very popular way to go because it does make things easy for the user while still giving them the flexibility to do advanced things like specify what the lifetime of data is, when to evict, and things like that. And then, of course, one of the more popular methods of doing a burst buffer here in the US, and we see this in our largest systems, the top 1 and 2 system, in fact, on the top 500 list to go with this architecture, is just putting flash in every compute node. So this has a lot of performance benefits in that it's the absolute highest performance you can get. Because your flash is directly attached to every compute node, there's no contention because it goes straight from your compute node memory right into your flash device. And then asynchronously, it drains from your node local flash device to the parallel file system on the back end. So there's extremely high performance, extremely low latency, no shared resource contention because everything is directly attached. But there is the added challenge of shared file I/O being extremely difficult because if you have a job that has written data out, but that data must be read by a process that's running on a different compute node, you suddenly have to synchronize data between compute nodes and you lose a lot of the benefits of having that node local flash. And there's also a major cost concern associated with this. So because you are putting flash in every compute node, you have this issue where if you add more compute nodes, you necessarily also have to add more flash. So whether you need it or not, you have to get the performance and the capacity of flash, and you really have to lock in that ratio, which might result in some suboptimal configuration in terms of the performance and the price you're willing to pay for it. And then finally, a very subtle point in this architecture is that it makes the scheduling of jobs a little bit more difficult. Because if you use the staging mechanism to asynchronously stage your data into a compute node before your job runs, your data is already in place. So that's good if your job will run when it's supposed to run, but if another job somewhere else in the system aborts abnormally and suddenly there's a lot of compute nodes free, you have no opportunity to backfill because your data is not there where it can instantly launch your job and access that node local storage. So it does make backfilling scheduling very difficult. And as I said before, this is a pretty popular way to go. So the Summit system and the Sierra system at Oak Ridge National Labs and Lawrence Livermore National Labs respectively use this. And the software, one of the software options that is available to make use of this is called BISC-FS from IBM. And the Tsubame machine in Japan also uses this architecture. And they're using BGFS using the on-demand feature to dynamically instantiate parallel file systems along with your compute node allocation. And then finally, I'll say that the newest option is just getting rid of the idea of a burst buffer entirely and just doing all flash. Just put flash everywhere. Get rid of the I/O fabric, get rid of the storage node, the I/O nodes in the middle, and just integrate flash directly on your network. And this might seem a little crazy in terms of you have to buy a lot of flash to do this, but at NERSC we just recently announced our Perlmutter system, which deploys this architecture as it's seen right here. So we'll be deploying 30 petabytes of all-flash Lustre directly on our compute node fabric. And this has many of the same benefits that we talked about before in the fabric-attached flash. So there's very flexible usage models. And in the particular case of just installing Lustre directly on the flash, it looks no different than a parallel file system as it's known to users today. So there's minimal transition effort, but a downside is it does still make the system susceptible to jitter because your I/O traffic is traversing the same network as your compute traffic. So having good quality of service is kind of essential to make this really successful. And also, this is perhaps the least developed in a software sense, in that the Lustre file system and every other parallel file system for that matter was really designed for spinning media. So it's not clear that if you put them on flash, they'll automatically get all the benefits of flash. They'll work faster, but you'll probably still be leaving a lot of the performance of the underlying flash on the table until the software catches up with the capabilities of the hardware. And as I said before, we will be deploying this at NERSC in 2020. So really, it makes sense to deploy flash in systems for high I/O performance. You just get the better performance and the better value of buying a storage media that's specifically made for performance rather than capacity and performance. But it does add a lot of extra components in your system. So instead of just spinning disks, you don't have to worry about a new media type. You might potentially have to worry about new node types if you do this fabric attached flash. And it adds a lot more complexity in understanding how performance works because of all these new components. And when problems arise, I'll say it becomes more challenging to understand why that problem is happening. Because instead of just understanding a Lustre file system, for example, you now have to understand all of the flash that's in between the compute and the data and understand where things might be going wrong. And there's no shortage of tools that help us understand what's happening at every single step in the storage hierarchy here. But as of today, it really is on a storage expert to understand how to use these tools. And when something goes wrong, understand the output from every single one of these, understand what it means in the greater context of the system architecture, and debug it. And that's a lot of effort. Storage experts are hard to come by, and they're very expensive. So ideally, we would have a better way of getting a good sense of storage performance problems in the deepening storage hierarchy when you do have flash and spinning disk in the same system. So at NERSC, part of my time is spent working on a research project called Tokyo, which stands for the Total Knowledge of I/O framework. And what this is, in practice, is it's implemented in Python. And the idea here is not to be a completely new monitoring framework. Rather, use all the tools that already exist. So, your favorite Lustre monitoring tools, your favorite block level tools, your DDN DirectMon or DDN Insight. Use everything that you've got and use this Python framework to just make it easier to pull all of that into a single place. So it doesn't replace the need for an I/O expert, but it makes that I/O expert have to do a lot less work to understand what's happening across all of the tools and all of the components on the system. So it really is just an abstraction layer that lets you write portable analysis tools without having to know the exact implementation details of every single one of those tools that understands just one part of your storage system. And this is actually a very useful approach. So we've been working on this for a couple of years, and one of the simplest examples of things it can do is that right now at NERSC, we use this to monitor both our Lustre file system and our burst buffer, and we can look at the loads on both of those storage systems at the same time. So this allows us to see, for example, the asynchronous stage in and stage out to our burst buffer. So the shaded in gray region here is a period in time when a job is running, and it does a typical checkpoint restart workflow where at the beginning of the job it has to read in a lot of data, and at the end of the job it flushes all of that back out. And meanwhile, in the Lustre file system load, as is showed in these dotted lines, there's a lot of background up and down, which is just the effect of every other job running on the Lustre file system. But because we have the burst buffer, we can stage in the data to the very quiet and very high performance burst buffer before the job begins, so that as soon as the job starts, it has immediate access to all flash and all the performance afforded by flash. And after the job ends, the user is no longer charging time, the data can be asynchronously staged back out, and we can see the benefits of the burst buffer here in that during the job runtime, the solid line, which is the burst buffer traffic, is right. There's no jitter going on. And then you can take this a step further and do some pretty sophisticated analysis by taking data from across the storage system. And this is just a highlight or a preview of a talk I'll be giving tomorrow in the technical program, where we were looking at storage performance as it varies over the course of an entire year. And by looking at all the different components, we could characterize what the sources of performance variation were in practice. And we found that contention, which is usually blamed for mysterious performance loss in I/O, is actually only part of the answer. And there's a number of other factors that cause performance variation in production file systems. So with that, I will just leave you with some takeaways here. And for more info, I encourage you to visit these links or feel free to ask me any questions. Thank you very much.